Hello everybody and welcome to Chapter 7 of Section 1. In this chapter, we are going to talk about the last major category of bias, the confounding bias. Specifically, we are going to define the confounding bias, then we're going to go over some examples of confounding bias, and we're going to finish off by going over all the different techniques used to control for the confounding bias. So by now you should be familiar with this table. We have already covered all the major kinds of errors and bias in research. I have left this kind of bias for last because it is somewhat different than the other two major types of bias. Unlike measurement bias and selection bias, confounding involves a third variable, which is also called a confounding variable. This third variable is called a third variable because it is not part of the two main study variables, which are the independent variable or exposure variable and dependent variable or outcome variable. Another major difference between confounding and the other kinds of bias is that various statistical analysis can be performed to control or minimize the risk of confounding bias. Remember, in selection and measurement bias, there aren't really that many statistical tests that you can do to remove the bias once the data has been collected. The main way to avoid these kinds of bias is to ensure that the study data and study sample are obtained in a way which minimizes the risk of bias. But once the data has been collected, there isn't much you can do. Well, when it comes to confounding, there are several statistical techniques which can identify potential sources of bias and even control for them. Overall, confounding bias is a concept which many students have trouble understanding, and yet it appears very frequently in board exams. In this chapter, I am going to break down confounding and the methods to control for it in the hopes that it'll help you grasp this topic once and for all. So what is confounding bias? The confounding bias is a measurement error which occurs when there is no association between the exposure and the outcome, but there are variables other than the exposure variable which are associated with the outcome variable and are creating a spurious or false association between the exposure variable and the outcome variable. In other words, the independent variable by itself does not produce the dependent variable. However, the independent variable for some reason may coexist with another variable which does produce the dependent variable. This variable is referred to as a third variable or confounding variable. Let's conceptualize this with an example. Let's imagine you want to know if variable A is associated with variable D. In other words, does the presence of variable A lead to variable D? So in order to do this, you design a study which looks like this. You recruit a group of individuals that has variable A, and you call this group the experimental group or exposure group. You also recruit another group of individuals who lack variable A. You call this group the control group. You then wait and see if the patients with variable A develop variable D more frequently than those patients which lacked variable A. You then wait and then reassess the patients for the presence of variable D, and you get these results. So right off the bat, it seems like your hypothesis was correct, because those patients with variable A had a higher frequency of variable D. However, upon further investigation, your statistician tells you that the subjects in the experimental group also had a variable called variable B in addition to variable A. The statistician proposes that maybe it was variable B that caused variable D, and in reality, variable A may not be associated with variable D. So in order to determine what variable caused the outcome, you split the experimental group into two groups based on the presence of variable B. Your second analysis then looks like this, in which you have grouped all the individuals which had variable A and lacked variable B. If you see that these individuals also have a high frequency of variable D, then you can conclude that variable A alone causes variable D because variable B was not present in this group. So when you get the results of this analysis, you see that all the patients which lacked variable B and only had variable A failed to develop the outcome variable D. Therefore, you conclude that variable B was a confounder in your study and variable A was not associated with increased risk of variable D. What we have described here is called stratification, and it is commonly performed to rule out confounding bias. We are going to talk about stratification more in just a minute. So basically, a confounder is a variable which is different from the exposure and outcome variable that causes the outcome variable independently of the exposure variable. In this example, variable B caused variable D independently of variable A. In other words, variable A did not cause variable B. Variables A and B just happened to occur together. An important point to understand regarding confounding is that the exposure variable never causes the confounding variable. The exposure variable and confounding variable may tend to occur together, but they are not causally associated. If the exposure variable did cause the confounding variable, then this variable would actually be an intermediate variable and not a confounder. In this situation, the exposure would truly be associated with the outcome via an intermediate variable, since the exposure causes the intermediate variable and the intermediate variable causes the outcome variable. However, in confounding, this is not the case, because the exposure variable does not cause or create the confounding variable. They just tend to occur together. Now let's talk about this in terms of our example. If variable B is more common in subjects that have variable A, and variable B is associated with variable D, then wouldn't variable A be associated with variable D? No. Variables A and B can occur together, but this doesn't mean that variable A alone is causally associated with variable B. In other words, just because variables A and B occur together doesn't mean that variable A causes variable B. For example, people who smoke also tend to drink more coffee, and in the past, studies which aim to look at the effect of coffee on lung cancer often showed a positive association. However, when subjects who only drank coffee and didn't smoke were analyzed, no association was found. Therefore, smoking was a confounder. So while drinking coffee and smoking tend to occur together, this doesn't mean that drinking coffee causes you to smoke, which causes you to have lung cancer. The exposure doesn't necessarily cause the confounding variable. The reason I am repeating this so much is because students often don't understand the relationship between the confounding variable and the exposure and outcome variables. In order to successfully grasp this topic, you need to understand the relationship between the variables. So in summary, what you absolutely need to understand here is that in confounding bias, the exposure never causes the outcome. That is, the exposure is not associated with the outcome, even though it may seem like they are associated. This is a very common figure which is used to explain how confounding works. If you have searched up confounding in the internet, you are bound to have seen an image like this. Let's take this opportunity to explain this image. In order for a third variable to be considered a confounding variable, it needs to be associated with both the exposure variable and the outcome variable, but it must not be in the causal pathway between exposure and outcome. In other words, A cannot cause B, because if A causes B and B causes D, then A can be said to be associated with D via an intermediate variable B. But this is never the case in confounding, as we just said. In confounding, the exposure is never in any way associated with the outcome. So if the exposure variable A cannot cause the confounding variable B, then what relationship does the confounder have with the exposure variable? Well, the way that I like to think about it is that B is associated with A via a coexisting association. That is, A and B frequently coexist, but A does not cause B. For example, smoking and drinking coffee are variables which frequently coexist. That is, people who smoke tend to also drink coffee, but drinking coffee by itself does not cause people to smoke more. On the other hand, what relationship does the confounding variable B have with the outcome variable D? As we said before, the relationship between the confounding variable and the outcome variable will always be a causal association. That is, B causes D, which is represented by the purple arrow. In this example, the purple arrow represents causal associations, while the green double arrow represents coexisting associations. So in summary, the confounding variable is associated with both the exposure variable and outcome variable, but the relationship between the confounder and exposure is different from the relationship between the confounder and the outcome. This is key to understanding confounding. So now that we understand the relationship between the variables, let's talk about the requirements required for a variable to be considered a confounder. There are 3 requirements for a variable to be considered a confounder. First, the confounding variable must be causally associated with the outcome variable. In other words, the confounding variable must cause the outcome variable. This is pretty easy to understand. If the confounder is not associated with the outcome, then it cannot create the false association between the exposure and the outcome, which is seen in confounding. Second, the confounding variable must be related with the exposure variable in some way other than causally. That is, the exposure variable cannot cause the confounding variable. This is also easy to understand because if the exposure variable causes the confounding variable and the confounding variable causes the outcome, then basically the exposure variable is associated with the outcome variable indirectly. However, as we have said multiple times, this is never the case in confounding bias. In confounding bias, the exposure is never in any way associated with the outcome variable. Third, the confounding variable must be unequally represented between the exposure groups and control groups. Otherwise, the effects would cancel out. Again, this is easy to understand. If your control group has the same amount of confounding as in the experimental or exposure group, then when you compare them, you will not notice any differences in the effects because the effects cancel out between the groups. This is why randomization is an effective method for controlling for confounding, because you are trying to balance out any potential confounding variables equally between the control and experimental groups. I hope this explanation helps you understand the concept of confounding, which is extremely important. I highly recommend that you commit this slide to memory. It is extremely important to recognize the 3 requirements required for a variable to be considered a confounder. Now let's consolidate our knowledge by looking at some examples. A cohort study is performed to determine if major surgery requiring general anesthesia is a risk factor for coronary artery disease. Researchers looked at the hospital records of patients who underwent major surgery requiring general anesthesia and then looked up to see if those patients later developed coronary artery disease. Initial analysis of the data indicated that major surgery requiring anesthesia was associated with increased risk of coronary artery disease. Further analysis of the data revealed that most of the patients in the exposure group tended to be older than those in the control group. What is a potential confounder in this study? Okay, so immediately there is a red flag here. The red flag is that the control group and exposure groups differed significantly based on age. The exposure group, or the group of patients who underwent major surgery with anesthesia, tended to be older than the control group, or those individuals who didn't undergo major surgery. Since we clearly know that advanced age is associated with increased risk of coronary artery disease, then a major concern for this study is whether old age was a potential confounder. This is suggested by the fact that most of the patients in the exposure group were older, and this makes sense since older people tend to require more invasive procedures such as major surgeries. We would need to perform stratification in order to confirm if age was a confounder. However, based on this information, age is a potential confounder in this study. This is because age is an independent risk factor for coronary artery disease. As people get older, they tend to have higher amounts of coronary artery disease. Next example. A study is performed to determine if weight-bearing exercise is associated with increased risk of cerebrovascular disease in adults over 60 years of age. Initial analysis shows that weight-bearing exercise is associated with increased risk of cerebrovascular disease in adults over 60. The patients with hypertension are identified, and a second analysis is performed that does not include the patients with hypertension. This analysis reveals no statistically significant association between weight-bearing exercise and cerebrovascular disease. Does this study suffer from random error, selection bias, measurement bias, or confounding bias? Alright, so the issue here is that there seems to be an association between weight-bearing exercise and cerebrovascular disease in older adults. However, when the subjects with hypertension are removed from the analysis, this association seems to disappear. What the researchers in this question stem have done is called stratification, and it is the same thing that we mentioned in example 1 of this chapter. The problem here is that hypertension is a confounding variable in the association between weight-bearing exercise and cerebrovascular disease. This makes a lot of sense because we know that hypertension is a risk factor for cerebrovascular disease. Therefore, when patients without hypertension are analyzed, there is no association between weight-bearing exercise and cerebrovascular disease. Therefore, the exposure is not really associated with the outcome. Instead, it is the confounder, hypertension, which is associated with the outcome and is creating the false association. Therefore, this is an example of confounding bias, and the confounding variable in this case is hypertension. Okay, so now that we have a solid understanding of confounding, let's talk about some common techniques for controlling for the confounding bias. There are several methods used in health research to minimize the risk of confounding bias, and the choice between what method to use depends on the type of study and the type of data being analyzed. It is also important to realize that no method fully eliminates the risk of confounding bias, and there are disadvantages to each method. So what are the most common techniques for controlling for the confounding bias? They are stratifying, randomizing, performing multivariate adjustment, matching, and restricting. So what is stratifying? Stratifying involves identifying variables other than the exposure and dividing the study population into strata based on those variables. One strata has a variable and the other does not, and then seeing if the association between exposure and outcome changes in each strata. This is the technique which we talked about in example 1 and example 3 of this chapter. The main disadvantage of this technique is that you cannot stratify for variables not measured. Variables not measured or unknown variables may still be a source of confounding bias. Now let's talk about randomization. Randomizing involves randomly allocating subjects into either an experimental group or a control group. The expectation is that any unknown variables that may confound the results are equally distributed between both groups and therefore cancel out. Unlike stratifying, this method also controls for unmeasured or unknown variables. The disadvantage is that you can only do this for experimental studies, aka randomized controlled trials. Let's move on to matching. Matching involves matching each subject in the exposure group with another subject in the control group who is identical to the subject in the exposure group except that they lack the exposure variable. The disadvantage of matching is that it is often difficult to match subjects in more than just a few variables. For example, sex and age. Now let's move on to restricting. Restricting involves identifying other variables that could potentially confound the study and then only recruiting subjects that lack those variables. The disadvantage of this method is that it sets restriction on the sample population and therefore increases the risk of having a sample population that is not representative of the target population. In other words, it increases the risk of the selection bias. The last technique for controlling for confounding is multivariate adjustment. In a multivariate adjustment, many variables other than the exposure are analyzed for associations with the outcome. The association between the exposure and outcome are then adjusted to not include the effect of the confounding variables. This method is very useful for identifying confounding variables and factoring out their effect from the association being studied. In fact, this is done very frequently. Typically, researchers will record many variables other than the exposure and adjust for these variables in their analysis or statistical model. The disadvantage is that it does not account for variables which are not measured. Again, multivariate analysis can only account for the effect of measured variables. unknown or unmeasured variables may still confound the effect being measured. Alright, now let's look at some examples. A study is conducted to determine if a high cholesterol diet is associated with increased risk of coronary artery disease. Researchers recruit a random sample of 600 people who have a history of confirmed coronary artery disease and provide them with a questionnaire in order to evaluate their average daily cholesterol consumption. For every individual recruited, researchers recruit another individual who lives in the same zip code, has the same gender and age, but doesn't have coronary artery disease, and provide them with the same questionnaire. What confounding bias prevention strategy did the researchers use? So the researchers here are conducting a case control study because they are looking for the outcome variable first and then searching to see if those subjects with the outcome variable were exposed to the exposure variable. Once the researchers identify a subject with the outcome, they match that person with a similar person who does not have the outcome and then determine if those with the outcome were more likely to have been exposed to the exposure variable. This technique is known as matching, and it is commonly used in case control studies. This technique aims to compare very similar individuals in order to ensure that if any confounding variables exist, they cancel out. Next example. A group of researchers are interested in knowing if consumption of processed foods is associated with increased risk of gastric cancer. The researchers are concerned that smoking is an independent risk factor for gastric cancer, and therefore it may confound the findings of their study. In order to eliminate the risk of confounding by smoking, the researchers decide to screen all the study participants for a history of smoking and then remove those that have a history of smoking from the study. What confounding prevention strategy did the researchers use? So in this scenario, the researchers have identified a potential confounder and then restricted people who have that confounding variable from entering the study or from contributing to the final data analysis. This is known as restricting, and the idea is to factor out any potential variables which may produce confounding bias. If none of the study subjects have a potential confounding variable, then confounding by that variable is impossible. Next example. A pharmaceutical company is interested in knowing if a newly developed drug decreases the progression of Alzheimer's disease. In order to do this, they recruit 1,000 subjects who meet criteria for early-stage Alzheimer's disease. They then split this group into two groups, one which will receive the experimental drug and one which will receive a placebo. The researchers use a computer which randomly assigns each of the 1,000 subjects to either the experimental drug group or the placebo group. What confounding bias prevention strategy did the researchers use? So this is a randomized controlled trial, and as the name suggests, randomized controlled trials are randomized. As we said earlier in this lecture, randomization is an effective way for minimizing the risk of confounding bias because any potential confounding variables are balanced between the groups and therefore cancel out. Remember, one of the requirements for confounding bias is that the confounding variable must be unequally represented between exposure and control groups. Randomization aims to ensure that the confounding variable is equally represented between groups. So here are the take-home points for this chapter. First, understand that the confounding bias involves a third variable or confounding variable which produces a spurious or false association between the exposure and outcome variables. Number 2. Understand that techniques exist to prevent confounding bias and control for the effects of confounding bias when they occur. And one last thing that I want to say again. In confounding bias, the exposure variable and outcome variables are never associated. Even though they might seem to be associated, they really are not. Thank you for watching, and see you in the next chapter.